All right, so the next post. Let's go back here. Minimal Rust kernel. In this post, we create a minimal 64-bit Rust kernel for the x86 architecture. We build upon a freestanding Rust binary from the previous post to create a bootable disk image that prints something to the screen. Okay, this will be exciting. This blog is openly developed on GitHub. Okay. When you turn on a computer, it begins executing firmware code that is stored in the motherboard ROM. This code performs a power-on self-test, post, detects available RAM, and pre-initializes the CPU and hardware. Afterwards, it looks for a bootable disk and starts booting the operating system kernel. On x86, there are two firmware standards, BIOS and UEFI. BIOS standard is old and outdated, but simple and well supported on any x86 machine since the 1980s. UEFI, in contrast, is more modern and has much more features, many more features, but is more complex to set up. So currently, we only provide BIOS support, but for support for UEFI is planned too. If you'd like to help with this, check out the GitHub issue. I wonder if it's been done by now. So somebody's working on it, right? At least as of 2020, which was a couple of years ago now. All right. Distraction. Almost all x86 systems have support for BIOS booting, including newer UEFI-based machines that use an emulated BIOS. This is great because you can use the same boot logic across all machines from the last centuries. But this wide compatibility is at the same time the biggest disadvantage of BIOS booting because it means that the CPU is put into a 16-bit compatibility mode called real mode before booting, so that archaic bootloaders from the 1980s would still work. But let's start from the beginning. When you turn on the computer, it loads the BIOS from some special flash memory located on the motherboard. The BIOS runs self-test and initialization routines of the hardware, then it looks for bootable disks. If it finds one, the control is transferred to its bootloader, which is a 512-byte portion of executable code stored at the disk's beginning. This is an interesting concept. Most bootloaders are larger than 512 bytes, so bootloaders are commonly split into a small first stage, which fits into 512 bytes, and a second stage, which is subsequently loaded by the first stage. Epic Blog says, I sense some 80s hostility coming from this guy. Well, yeah, I mean, this is just, there were limitations, right? Based on the available technology, so. But, you know, if you really had a problem with it, you should have started with UEFI, but maybe that would have made the whole thing too complicated. The bootloader has to determine the location of the kernel image on the disk and load it into memory. It also needs to switch the CPU from 16-bit real mode first to the 32-bit protected mode and then to the 64-bit long mode, where 64-bit registers and the complete main memory are available. Its third job is to query certain information, such as a memory map, from the BIOS and pass it to the OS kernel. Writing a bootloader is a bit cumbersome as it requires assembly language and a lot of non-insightful steps like write this magic value to this processor register. Therefore, we don't cover bootloader creation in this post and instead provide a tool named boot-image that automatically prepends a bootloader to your kernel. If you're interested in building your own bootloader, stay tuned. A set of posts on this topic is already planned. All right, I'll have to look out for that. But we're going to use the boot image, whatever that turns out to be. To avoid that, every operating system implements its own bootloader, which is only compatible with a single OS. The Free Software Foundation created an open bootloader standard called multiboot in 1995. The standard defines an interface between the bootloader and the operating system so that any multiboot compliant bootloader can load any multiboot compliant operating system. The reference implementation is GNU Grub, which is the most popular bootloader for Linux systems. To make the kernel multiboot compliant, one just needs to insert a so-called multiboot header at the beginning of the kernel file. This makes it very easy to boot an OS in Grub. However, Grub and multiboot standard have some problems too. They only support 32-bit protected mode, They're designed to make the bootloader simple instead of the kernel. Okay, both grub and the multiboot standard are only sparsely documented. That sounds familiar. Grub needs to be installed on the host system to create a bootable disk image from the kernel file. This makes development on Windows or Mac more difficult. Nice. Because of these drawbacks, we decided not to use grub or the multiboot standard. Okay. However, we plan to add multiboot support to our boot image tool, so it's possible to load your kernel on a grub system too. If you're interested in writing multiboot compliant kernel, check out our first edition of this blog series. UEFI. We don't provide UEFI support at the moment, but we would love to. If you'd like to help, please tell us in the GitHub issue. Right. So now that we know roughly how a computer boots, it's time to create our own minimal kernel. Our goal is to create a disk image that prints a hello world message. Hello world. Message to the screen when booted. For that, we build upon the freestanding Rust binary from the previous post. As you may remember, we built a freestanding binary through Cargo, but depending on operating system, we need different entry point names and compile flags. That's because Cargo builds for the host system, right? So we did the target, right? Installing Rust nightly. Rust has 3 release channels: stable, beta, and nightly. Rust book explains the difference. To manage Rust installations, I highly recommend RustUp. The nightly compiler allows us to opt into various experimental features by using so-called feature flags. For example, we could enable the experimental ASM macro for inline assembly by adding feature ASM. Note that such experimental features are completely unstable, which means that future Rust versions may change or remove them without prior warning. For this reason, we will only use them if absolutely necessary. Cargo supports different target systems to the target parameter. The target is described as so-called target triple, which describes the CPU architecture, the vendor, the operating system. Right, yeah, we did this last time, right? We set it up for, we're going to be doing, instead of the thumb V whatever, we're going to do this one. For our target system, however, we require some special configuration parameters, so none of the existing target triples fits. Fortunately, Rust allows us to define our own target through a JSON file. For example, a JSON file that describes this target looks like this. Okay, is this what we're going to be using? Most files are required by LLVM to generate code fields. Are required by LLVM to generate code for that platform. Epic Blog says 16 bits ought to be enough for everyone. I was just looking at the IBM 701, and I think that has, and this was from the 50s, I think that has 36 bits. I remember. Oh. Memory. Vacuum tube logic circuitry. 36 bits. Memory could be expanded by a maximum of 4K words. Right, so it was 2048 words of 36 bits each. Those are the olden days. Before my time, even. We also target x86 64 systems with our kernel, so our target specification will look very similar to the one above. Let's start by creating with a common content. You choose any name you like. Well, the one I like is the one they give, so I'm gonna use that one. I assume it just goes in the top level directory of my workspace. Right. Now that we changed the OS in the LLVM target and the OS field to none. So this is none here and this is none here because we will run on bare metal. We add the following build related entries. Linker flavor. Oh, we have to add these. Okay. Flavor. Wow. V. LD. LLD. And then we have linker, which is Rust LLD. This needs a comma. Okay. Instead of using the platform's default linker, which might not support Linux targets, we use the cross-platform LLD linker that is shipped with Rust for linking our kernel. Then we're going to add a paddock strategy. Abort. This setting specifies a target doesn't support stack unwinding on panic, so instead the program should abort directly. This has the same effect as panic equals abort option in our cargo.toml, so we can remove it from there. Okay. Note that in contrast to the cargo.toml option, this target option also applies when we recompile the core library later in this post. So be sure to add this option even if you prefer to keep the cargo.toml option. Okay. And then disable red zone. Is true. We're writing a kernel, so we'll need to handle interrupts at some point. To do that safely, we have to disable certain stack pointer optimization called the red zone, because it would cause stack corruptions otherwise. For more information, see our separate post about disabling the red zone. Epic Blog says it's kind of amazing to see image file headers that are larger than the entire memory of my first VIC-20. Yeah, the VIC-20 had what? 8K of memory? 3K of which was already used up by the basic operating system? Something like that? Shishak says many people hate red zone. Is because so what I'm thinking of the red zone is a region between stack sections that can be detected if you overwrite them. You could they're written with a pattern. Maybe I don't know what they are, but this is what I imagine that they are. Is that you write a pattern between stack sections, so you can see if you've overwritten a stack if the pattern has been stomped on. The features field disables target features. We disabled MMX and SSE features by prefixing them with a minus and enable the soft float feature by prefixing it with a plus. Note that there must be no spaces between different flags, otherwise LLVM fails to interpret the feature string. Yeah, so well, I'll read more, but I know why we disable it on the operating system I work on. Features, MMX, SSE, soft float. So adding soft float is probably going to make the OS bloat from 5K to much bigger, right? The MMX and SSE features determine support for the SIMD instructions, which can often speed up programs significantly. However, using large SIMD registers in OS kernels leads to performance problems. The reason is that the kernel needs to restore all registers to the original state before continuing an interrupted program. This means the kernel has to save a complete SIMD state to main memory on each system call or hardware interrupt. Since the SIMD state is very large, and interrupts can occur very often, these additional save restore operations considerably harm performance. To avoid this, we disable SIMD for a kernel. Shishak says red zone causes problem with hardware interrupt. That's why it's important to disable red zone. Okay. Yeah, I mean, that makes sense if the hardware is writing to your stack for you, maybe. It needs to not have to worry about it's not going to have logic built in to deal with red zone. Problem with disabling SIMD is that floating point operations on x86-64 require SIMD registers by default. To solve this problem, we add the soft float feature, which emulates all floating point operations through software functions based on normal integers. For more information, see a post on disabling SIMD. So putting it together, this is the whole thing. So now, hopefully I got all of that in there. Let's write that out before I forget. Compiling for our new target will use Linux conventions. I'm not quite sure why. I assume that's just LLVM's default. This means we need an entry point named start, as described in the previous post. We have that. Right? Note that the entry point needs to be called _start regardless of your host OS. We can now build a kernel for our new target by passing the name of the JSON file as the target. Oh, okay. Yeah, let's save that out. And then we can say cargo build target JSON. Error can find create for core. Okay, let's see if we get that same error. We do. We got others. but we do get the core problem. It fails. The error tells us that the Rust compiler no longer finds the core library. This library contains basic Rust types such as result, option, and iterators, and is implicitly linked to all no standard crates. The problem is that the core library is distributed together with the Rust compiler as a pre-compiled library, so it's only valid for supported host triples, but not for a custom target. If we want to compile code for other targets, we need to recompile core for these targets first. The build standard option. That's where the build standard feature of cargo comes in. It allows to recompile core and other standard library crates on demand, instead of using the precompiled version shipped with the Rust installation. This feature is very new and still not finished, so it's marked as unstable and only available in nightly Rust compilers. Is that still true? It requires at least Rust Nightly from 2020. Has this been merged into... Let's find out. Let's find out. So we're going to modify .cargo. Oh, we have to create it. Cargo config.toml. Now, why doesn't this go in the regular toml? So we're just going to put unstable build standard equals core compiler underscore built-ins. After setting the unstable build standard configuration key and installing Rust source component, where did we do that? Where did we install the Rust source component? In order to recompile these libraries, cargo needs to access the Rust source code, which we can install with Rust up component add Rust source. Okay. So this might take a little while. Rust up component. That doesn't have completion. Okay. Add Rust source. Oh, I must have done that already. Okay. I wonder what I use that for. So after this, and installing Rust source component, we can rerun our build environment. Okay. Let's try the build again. But it still fails. So yeah, so I just added this to the .cargo config toml. Did I do that wrong? That looks right. Maybe, so it must not be finding it. So maybe it needs nightly. It didn't say how to switch to nightly here, right? Shouldn't I just put a plus nightly on here or something? And here's more of that. So I missed a step. I thought I was trying to be super careful here. There's no nightly specified here, right? Shrishak says, I think Rust Up should have installed it by default. Maybe. Maybe that's something recent since this blog was written. But now I'm stuck here, right? Because it's only available on nightly. So I should I be doing plus nightly here? Or does it go here? You can tell I don't normally use nightly, so. Nope. Oh no, just built like this. All right, so what did I miss? I'm specifying this as the target. I don't have nightly installed for that target. Okay, it doesn't. So this is how I added this target, but there's no target to add for this special JSON version. Rust up show. Yeah, so I added this, right? And this is my default, and this is the WASM I'm using for my roguelike. But this is a custom target, I guess. What am I missing from here that's preventing me from getting this to recognize the .cargo config.toml file? Epic Blog says there's another flag along the lines of -- toolchain nightly you can add. SureShack says create a Rust toolchain toml file and put the toolchain channel equals nightly. SureShack says it recognized cargo file by default. Put on verbose. Okay. Ooh, that was a lot. So it ran this. So I'm going to create the Rust toolchain toml in a second. I just want to see what the output was here. Do you see a toml anywhere? No, it's not doing it down here. So I don't see it reading that. Oh, let's try this. All right, we'll create a new toml file. Get rid of this, and we'll put tool chain channel equals nightly, and then see what happens if I do a build. Okay, so now it is doing it for this. So is this an omission from here, or did I just not read correctly what I needed to do? Because now it's installing it's installing everything for this. Oh, and it still didn't work. It's unable to build with the standard library. But I don't want to build it with the standard library. I can do this, right? I want to build it for this target. Okay. Why is it doing this? I'm confused. By the way, do you have nightly installed? Well, let me see, what was the output of that other rust up show command? Oh, it's gone now. What happened to it? All right, so it built. Looks like it built. Right? So we have a BlogOS. So why did it have to download these guys? Did compiler built-ins use these? I understand compiler built-ins. There's core, there's compiler built-ins, workspace core, and now we should have target this x86-64 BlogOS. Debug. How big is it now? Oh, it's not that big. I guess since we're not using any floating point numbers yet, maybe it didn't pull in the floating point number. SureShack says, yes, you need those crates to build a standard library. Oh, interesting. So these random crates. So if GitHub goes down, you can't use Rust. What does Gimli do? Oh, is that for the dwarf format files? That's okay. That's cute. All right, so we did this. It was able to compile these things. We have core version 0.0.0, Rust Standard Workspace Core 199, and we have 199. Compiler built-ins 0132, we're up to 0173, and then BlogOS is version 0.1.0. Okay, so we're getting there. So we had to do that a couple extra steps. We created the Rust toolchain. Thank you, Shurshak, for that. And then thank you, Epic, also for the help there with the Rust up. And so toolchain nightly, I think. So let me move that here and see if that will also work. So this is an alternate approach. No, there is a cargo help build. Oh, plus tool. It says plus toolchain. Yes, wasn't I trying that before? Plus nightly build, and with this target. Yeah, cargo clean. So now it's building core and compiler built-ins. Still working on core. And now it's stuck. Okay. All right. So there we go. So this also works, but I think having this Rust toolchain avoids having to put the plus nightly on the command line. All right. So that's what I was missing, and that's what they need here, right? They need to add the plus nightly to this. Unless there was something I missed up above. I don't think I did. Target specification. That's what we created a JSON file. All right. Okay, so we got this working. Memory-related intrinsics. The Rust compiler assumes that a certain set of built-in functions is available for all systems. Most of these functions are provided by the compiler built-ins crate that we just recompiled. However, there are some memory-related functions in that crate that are not enabled by default because they are normally provided by the C library on the system. These functions include memset, which sets all bytes in memory block to a given value, memcopy, which copies one memory block to another, and memcomp, which compares two memory blocks. While we didn't need any of these functions to compile our kernel right now, they will be required as soon as we add some more code to it. Since we can't link to the C library of the operating system, we need an alternative way to provide these functions to the compiler. One possible approach for this could be to implement our own memset etc. functions and apply the nomangle attribute to them to avoid automatic renaming during compilation. However, this is dangerous since the slightest mistake in the implementation of these functions could lead to undefined behavior. For example, you might get an endless recursion when implementing memory copy for using a for loop because for loops implicitly call the into-iterator trait method, which might call memcopy again. So it's a good idea to reuse existing well-tested implementations instead. Fortunately, the compiler built-ins crate already contains implementations for all the needed functions. They're just disabled by default to not collide with the implementations from the C library. We can enable them by setting cargo's build standard features flag. Like build standard flag, this flag can either be passed in on the command line as a $Z or configured in the unstable table in cargo config toml. So we'll do that. So build, but first build standard features is equal to compiler built-ins mem. Built-ins. Built-ins. There we go. That's interesting. This one has an underscore, and this one has a hyphen. Support for the compiler built-ins mem feature was added only recently, so you need at least Rust nightly. Okay, we have that. Behind the scenes, this flag enables the mem feature of the compiler built-ins crate. The effect of this is that the nomangled attribute is applied to memcopy, etc. implementations of the crate, which makes them available to the linker. With this change, our kernel has valid implementations for all compiler-required functions, so it will continue to compile even if our code gets more complex. Set a default target. All right, to avoid passing the target parameter on every invocation of cargo build, let's just rebuild this just to make sure this is working. Yeah. Okay. Unix superhero. Thank you for the follow. So we're going to add this to our, so we're going to continue to add to this guy. We're going to add a build, and it's going to be target. It's going to be the file, right? Oh, the JSON stays on. Okay. This tells cargo to use our x86-64 blog.os JSON target when no explicit target argument is passed. Okay, so if I do this, I should be able to run build from here. Oh, I'm in a TOML file. Okay. Okay, I think it built. It doesn't say what the target was, but I'm assuming it was the correct target. I should be able to say cargo clean -p blog os. Nope. Okay. I guess not. I must be misunderstanding the clean thing. All right. This means that we can now build our kernel with a simple cargo build. For more information on cargo configuration options, check out official documentation. We're now able to build a kernel for a bare metal target with a simple cargo build. However, the start method entry point, which will be called by the bootloader, is still empty. It's time that we output something to the screen from it. The easiest way to print text from the screen at this stage is the VGA text buffer. It's a special memory area mapped to the VGA hardware that contains the contents displayed on the screen. It normally consists of 25 lines that each contain 80 character cells. Each character cell displays an ASCII character with some foreground and background colors. The screen output looks like this. We will discuss the exact layout of the VGA buffer in the next post, where we write our first small driver for it. For printing hello world, we just need to know that the buffer is located at address 0xb8000, and that each character cell consists of an ASCII byte and a color byte. Implementation looks like this. Okay. So we're going to do another no mangle. We have the start. Let VGA buffer is equal to hex B8000 as star mu8 for I byte. Oh, I got to put the static here. Static hello. There's an array of U8s. Right, that looks good. And hello, iter, enumerate, unsafe. Ooh, unsafe. VGA buffer offset I as I size times 2 equals byte. VGA buffer offset I as I size times 2 plus 1 is equal to OXB. I assume this is the color bit. And then we still want a loop at the end of that. Okay. First, we cast the integer B8000 into a raw pointer. Then we iterate over the bytes of the static hello byte string. We use the enumerate method to additionally get the running variable I in the body of the for loop. We use the offset method to write the string byte and the corresponding color byte. B is light cyan. Oh, too far. Note that there's an unsafe block all around memory writes. The reason is that the Rust compiler can't prove that the raw pointers we create are valid. They could point anywhere and lead to data corruption. By putting them into an unsafe block, we're basically telling the compiler that we're absolutely sure that the operations are valid. Note that an unsafe block doesn't turn off Rust's safety checks. It only allows you to do 5 additional things. And we'll take a look at those later. I want to emphasize that this is not the way we want to do things in Rust. It's very easy to mess up when working with raw pointers inside unsafe blocks. For example, we could easily write beyond the buffer's end if we're not careful. So we want to minimize the use of unsafe as much as possible. Rust gives us the ability to do this by creating safe abstractions. For example, we could create a VGA buffer type that encapsulates all unsafety and ensures it's impossible to do anything wrong from the outside. This way we would only need minimal amounts of unsafe and can be sure that we don't violate memory safety. We will create such a safe VGA buffer abstraction in the next post. Running our kernel. Oh, we get to run it. Now that we have an executable that does something perceptible, it's time to run it. First, we need to turn our compiled kernel into a bootable disk image by linking it with a bootloader. Then we can run the disk image in QEMU virtual machine or boot it in real hardware using USB stick. To turn our compiled kernel into a bootable disk image, we need to link it with a bootloader. As we learned in the section about booting, the bootloader is responsible for initializing the CPU and loading our kernel. Instead of writing our own bootloader, which was a project on its own, we use the bootloader crate. This crate implements a basic BIOS bootloader without any C dependencies, just Rust and inline assembly. To use it for booting our kernel, we need to add a dependency to it. Okay, so in our TOML, bootloader equals, should I just grab the latest instead of, I don't know if 098 is the latest. Yeah, let's save these changes. Cargo add bootloader. Adding the bootloader as a dependency is not enough to actually create a bootable disk image. Yeah, they're up to 10.12. Okay. The problem is that we need to link our kernel with the bootloader after compilation, but Cargo has no support for post-build scripts. And to solve this problem, we created a tool named boot-image that first compiles the kernel and bootloader and then links them together to create a bootable disk image. To install the tool, execute the following command. Okay. For running boot-image and building the bootloader, you need to have the LLVM tools preview rustup component installed. You can do so by executing rustup component add LLVM tools preview. All right, I will do that in a second, as soon as boot image is done building. There we go. So rustup component add LLVM tools preview. Okay. After installing boot image and adding the LLVM tools preview component, let me just rust up show. Okay, so it doesn't show, that shows the tool chains. Is there a way we can show the all the components? Okay. We can create a bootable disk image by executing cargo boot image. Warning, cargo manifest dir environment variable not set. An error occurred while trying to build the bootloader. Okay. No package metadata bootloader target key found in cargo toml of bootloader. Shrishak says rustup component list is the way to list all your components. Okay. Thank you. There it is. Okay, so we have a problem, and this is assuming it works, right? This says it worked. Look at that. Unfortunately, it did not work. Let's see if we can find this error message. I mean, an error occurred. Oh, there's a typo. Okay. I don't see, maybe I do need to specify this version. Let's try that. Maybe I'm getting ahead of myself here. Let's do the 9.8 version. Right? Okay. So I wonder what's different. Okay, so here's configuration. This is what they were looking for, package metadata boot image, right? Way back here. Yeah, package metadata bootloader. Oh, this is bootloader target. This is boot image. So there must be some key I need to add to my cargo toml to get the latest version of 10.12 to work. So meanwhile, let's just work with, because this looks like it worked. Ah, and now it's much, much bigger, isn't it? Right? This is 2 megabytes instead of the 5K it used to be. All right, well, we got it to build. That's the good news. After executing the command, you should see a bootable disk image named bootimage blogos.bin. Oh, this is only 64K. Less than 64K. Okay, so I wonder what the difference is here. Where was I? Okay, you can boot it in the virtual machine or copy it to a USB drive to boot it on real hardware. Okay. But I can boot it in QEMU. Okay, so now I can use QEMU. QEMU system. x86 64. Right? Dash drive. Format equals raw, comma. File equals target. x86. Oh, I can't do that. BlogOS. Debug. Boot image. Right? Oh, this scrolls off the side here. .bin. Okay, that's all we need to do. And we have a warning. TCG doesn't support requested feature. Something, something, something. This opens a separate window that looks like this. All right, are we ready? SureShack says, by the way, LSDSLH might be helpful. Oh, yeah, but I'm so old school. Look at that. We have a booting operating system, and it printed Hello World in there. I wonder if I should make a roguelike in this then. Ha! The entire operating system is just a roguelike. Epic blog cheers. Yay! Okay. Yeah, so we actually have QEMU loads our binary, it runs the start thing, and it prints Hello World to the screen right at the beginning. And it matches this, so I think we're doing well. And I just lost my mouse. That's fun. Okay, let me go into this. Can I hit force quit here? It's a good thing I was able to use it with the keyboard because I lost my mouse. I couldn't do anything with it. Okay. Terminating on single 15. Yes, very good. RogueOS will wipe your hard drive if you die in game. Ha! That would be brutal. SureShack says, call your cat. Our cats like to eat bugs. They go after bugs. I haven't seen them get a mouse yet. They do like to watch the chipmunks outside, though. They stare at them very intently as the chipmunks dart about doing their chipmunky things. The real Epic Blog says it's the real meaning of a roguelike. Yeah, like the true meaning of Christmas, this is the real meaning of a roguelike is you lose your computer if you die. So real machine. It's also possible to write it to a USB stick and boot it on a real machine. Yeah, using DD to write it to a USB stick. So you basically just overwrite the entire contents of the USB stick, blowing away whatever file system was on there. I'm not going to do this on stream because it won't work. Using cargo run. To make it easier to run our kernel in QEMU, we can set runner configuration key for cargo. Okay. Cargo. So now we're going to add target and then quote CFG target OS equals none. Single quote, close bracket, runner equals boot image runner. The target something table applies to all targets that have set the OS field of their target configuration to none. This includes our target. The runner key specifies the command that should be invoked for cargo run. The command is run after a successful build with the executable path passed as the first argument. Boot image runner command specifically designed to use as a runner executable. It links the given executable with the project's bootloader dependency and then launches QEMU. Now we can use cargo run to compile our kernel and boot it into QEMU. Let's try that. All right, look at that. I'm not going to click in the window because I'm going to lose my mouse. There should be a way to... Oh, I can't click any of these menu options. Oh, because it's running infinite loop. Maybe that's why. Maybe it needs an interrupt in order to process clicks. Yes, I'm sure I want to quit. Okay. SureShack says DD is the most dangerous command. It is. You can blow away anything and everything with it. All right, so I think we're at the state. We're good. We get status. Git add. Do I dare do a dot? I'm going to do a dot. Yeah, git commit -m. Boots prints hello world and runs builds for QEMU and runs. Yeah, let's just do that. And then I'll create a repo off screen and push it up there. All right.